Okay, so let's continue on from the topic I introduced last class, which is Thevenin and Norton equivalent circuits. So, in this example circuit here, similar to the last illustration I made in the last class, this example circuit, we are asked to find the voltage across R6. And of course, if you're trying to find a particular value for R6, if the value for R6 keeps changing, then you have to perform the analysis again and again and again. So the whole point of using a equivalent circuit, the whole point of the Thevenin theorem was that you only analyze the circuit once between the terminals where R6 is connected, and you can represent the entire circuit as one single voltage source in series with the resistance. So you would take this circuit and you can represent it as one single voltage source in series with the resistance. So this circuit is known as the Thevenin theorem. This theory was presented in the late 1800s, around 1880s, 1890s. And then a few decades later, there were some engineers working at Bell Labs. They were using Thevenin's theorem and performing some research for their circuits, audio engineering. They were finding it difficult because they work with a lot of current sources in audio engineering, audio circuits. And so there was an engineer by the name of Edward Norton, not the actor, he's not that old. And he postulated his own theory saying that you could take Thevenin's theorem, similar to Thevenin's theorem, you could take the large circuit, analyze it between the same terminals, and you can represent it with a current source in parallel with the resistance. And that theorem came to be named after him. So named as Norton theorem or Norton's theorem. The current source, IN, came to be known as Norton's current. The resistance is still the same, RTH, Thevenin resistance. Sometimes, if we are looking solely at Norton circuit, we might refer to as Norton resistance. But for all intents and purposes, technically, that resistance is still RTH. Okay. So if you remember chapter 1, voltage source, real life voltage source, have a resistor in series, current source will have a resistor in parallel. So a large circuit can be represented by a voltage source in series with the resistance, and it could also be represented by a current source in parallel with the resistance. Okay. So those are two circuits, Thevenin equivalent circuit and the Norton equivalent circuit, right? Now, if A equals X and A also equals Y, then we can write that X equals Y, right? Logically. So Thevenin circuit is equivalent to the larger circuit. The Norton circuit is also equivalent to the larger circuit. Hence, the Thevenin circuit and the Norton circuit are equivalent to each other. So these two are equivalent to each other. And from that logic flows the concept of source transformation. If we have a voltage source in series with a resistor somewhere in the circuit, you could transform it into a current source in parallel with the resistance and vice versa. You can go from here to here and from here to here. This, again, this is a technique that you can actually use to simplify your circuits. We will take a look at a couple of examples of source transformation after we get done with Thevenin later on in this chapter. It is not a technique that I personally prefer to use a lot because it can get complicated. If you look at the circuit above, actually let's go to the bigger one. If you look at this circuit right here, we can see that this voltage source in series is in series with R1, right? V1 and R1 are in series. They're connecting at those 2 points. So if we wanted to, we could transform this voltage source into a current source. In some cases, it makes analysis easier. It doesn't seem so right now, but when we look at these examples, it will make it easier. So we could transform this. If we go here, possibly we can transform V3 and R6 also. But what you're going to do, what you have to do is you have to remove those components from the circuit, you transform it, and you plug it back into the circuit. And to do that requires some sort of recognition. And I often make errors when I try to do that, especially if the component is somewhere in the middle of the circuit. It's not possible to transform this at all because you have a current source, but there is no resistor in parallel with it. And so we cannot transform the current source at all. Okay, so I just wanted to introduce that topic, and then we look at some examples later after we get done with everything. But that's where the concept of source transformation comes. The Thevenin circuit is equivalent to the larger circuit. Norton circuit is also the same, and so they are both equivalent to each other. Yes. Oh, you mean in this circuit? Yes, yes. So R1, if I was to transform V1 into current source, let's say I V1 or something, then R1 remains the same. Yes, remain the same. Also, we have voltage, resistance, and current. What can we use to describe the relationship between all three of them? Ohm's law, right? And so source transformation depends on this equation. VTH is Norton current times RTH. So source transformation, if you have a voltage with a resistance, you use this equation to find IN. If you have IN and RTH, you can use it to find VTH. So now, I've been talking about this as an important concept. So let me give an example of where and how and why we would use a Thevenin and Norton circuit. And for that, I'm going to go to the end of the chapter. To maximum power transfer theorem. Maximum power transfer theorem states that if you have a circuit, if you have a load RL connected to a circuit, and you want maximum power to be transferred from the circuit to the load, then the load should have a resistance that is equivalent to the Thevenin resistance of your driving circuit. Meaning the Thevenin resistance of this circuit, RT, should be equal to the load resistance, RL. Okay, and under those conditions, maximum power will be transferred from circuit 1 to the load. So here, this is basically represented by this Thevenin voltage and Thevenin resistance. RL will have some current being supplied from the source, from the driving circuitry. In order for maximum power to reach there, RL has to equal RTH. There's a simple derivation behind this. I won't go over the derivation, but it starts from VT is IL times RT plus RL. And then, of course, power is given by V square over R. We plug in the values in there. There's the derivation is there in the book. That's not really that important. I don't want students actually like trying to memorize, but understand how we derive the things. So we find the voltage, plug it in here, and then plug it into this equation, the power equation. Power will be max when the slope goes to 0. So we set it to 0, and you reduce it, and you obtain PL max is VTH square or 4 times RTH. That's the maximum power that will be transferred at the output. So the maximum value of RL power cannot exceed this value, will not exceed this value. Now, in real life, the application is actually quite common. We all use it every single day. A speaker. And in a speaker, the driving circuitry is more likely than not an amplifier. The amplifier will have its own driving circuitry known as a preamplifier or a preamp. Preamp actually takes an incoming signal, makes it slightly stronger, and then passes it on to the amplifier. The amplifier sets the output, goes to the speaker. Anyone ever take a look at the spec sheet of an amplifier or a speaker or a headphones? Anyone? Do you notice what impedance it says for the speaker? So it's a very common thing. It's probably buried in the spec sheet at the end of the manual, but you Google any AVR, any audio video receiver off the shelf, the market from any manufacturer. At the end, it'll tell you the power spec. It'll tell you 100 watts per channel driving into 8 ohms. And what they're telling you is that the amplifier, in order for maximum power to be transferred to the speaker, your speaker needs to have 8 ohm impedance. Now, impedance is a term we will look at in chapter 5, but for now, think of it as resistance. Okay? Think of it as resistance. So the amplifier spec sheet, again, is telling you that in order for maximum power or for the amplifier to function correctly, your speaker needs to have an 8 ohm impedance, 8 ohm resistance, if you will. The earphones that we use, at least the wired ones, they have an impedance of 32 ohms. AirPods, I haven't looked it up recently, but I believe they were still 32 or maybe 16. They would either be 16 or 32 ohm impedance, 32 ohm resistance. The reason is all the manufacturers will design their devices, smartphones, tablets, what have you, to actually have an impedance or a Thevenin resistance of 8 ohms. So the amplifier, all manufacturers will have an amplifier that has a Thevenin resistance of 8 ohms at its output terminals. So when you connect a speaker with 8 ohm impedance or 8 ohm resistance at the amplifier terminals, maximum power will be transferred, or more efficiently will be transferred. Now, most manufacturers, the speakers and the amplifiers are 8 ohms. So as a consumer, if you go to buy something off the shelf, you don't have to worry about it. But if you buy something like custom made, well, not custom made, but if you guys separate pieces for everything, like a preamp, an amplifier, and a speaker that you're setting up yourself, then you need to pay attention to what you're purchasing. I once had a 4 ohm speaker that I was driving with an 8 ohm amplifier. I mean, I knew about it, but I kept the volume low, but somebody came in and turned it up high. And when you do that, you're trying to drive more power. So you're trying more current in there, the speaker coil would start burning. So until we started smelling smoke coming out, nobody realized what had happened. So it's a real life thing that, that does happen. But that's the most common real life example that I can give you of a Thevenin resistance. In your book, there is also an example of, and I like that example also. Anyone ever lived in a cold climate? Like a snowstorm, ice storm, you try to start the car. It doesn't start very quickly if the battery is old. The reason is the battery can be represented, the car battery can be represented as a Thevenin voltage and has its own Thevenin resistance, right? So in cold climates, the reaction, it's an electrochemical battery cell, right? So the reaction will take place a little bit slowly. So when it takes place a little bit slowly, the Thevenin resistance of the battery is high. When the Thevenin resistance high, power is not transferred. When this goes high, power is reduced. That's why you would have trouble starting a car in very cold weather first thing in the morning. And to do that, a car battery will have a spec known as cold crank amps. Basically, how many amps it can supply when it's really, really cold to crank your engine. Anyway, so coming back from a real life example, that's, as I said, electrical engineering, it's a very important concept. It has many different applications. These are two of the most common applications that we use in everyday life. As far as analysis goes, it is not new, right? You have performed this analysis before. You're going to find Thevenin resistance, you're going to find Thevenin voltage, and you're going to find Norton current. All three of these rely on the analysis techniques that you've already done. All you're learning, the only new thing that you're learning is the concept and how to set up the problem. And that's what I will go over in the slides. So now, these two slides, 25 and 26, again, you already have these. They're posted on Canvas, also in the class notebook. They go against my grain when I say, you should not have too many words on a slide. But this is an important point, so I make an exception for these two slides only. There are 8 points in here. Point 6, 7, 8 tell you exactly what you need to do to analyze the circuits for voltage, current, and resistance. And points number 5, 1 through 5 is basically how you're going to set them all up. The first things, First things first, if the question states analyze the circuit between, sorry, not between, as seen by a component, then you remove that component from your analysis, right? You take that component out of your analysis, as we saw in that example, right? So you remove it, and you're left with open terminals. And the rest of the circuit is here, of course. You're left with open terminals. You analyze the circuit between those open terminals and determine everything that you need to. Now, in your homework, in your textbook, most of the problems, there already are open terminals. You don't have to do anything. You don't have to modify the circuit in any way. You simply begin analyzing the circuit as it is between those terminals. Okay, so that's the first thing. Then you're going to perform 3 separate analyses. Okay, once for voltage, once for current, once for resistance. So 3 separate and independent analyses. All 3 of them are completely different because the 3 circuits that you analyze are all different. Okay. The voltage one is the easiest in the sense that you don't have to modify it at all. You just keep the output terminals open, you measure the output voltage, and that's it. For current, you need a pathway for the current to flow through. So you take the same terminals, you short it out, you measure the current through there, done. Thevenin resistance, all you need to do is short out all the terminals of the power supplies, measure Req at the terminals, and again, that's your Thevenin resistance. What I don't want students to do is to use Ohm's law to find Norton current directly from Thevenin resistance and Thevenin voltage. So when I say do not use Ohm's law, what I'm saying is do not use this. IN is VTH or RTH. Do not use this. Okay. You can use Ohm's law within your analyses to determine the values. That's fine. But at the higher level, I do not want anyone to use Ohm's law to find Norton current directly from here. There's 3 separate analyses. This problem, as I said, is going to be about 25, 30-point problem in your final exam. It will test a variety of topics. It's going to test a variety of topics. And finding the Norton current is one of them. Okay, it's a very important point. Again, I'll make sure that it's also listed on the question itself. Now, the analysis, again, as I said, you can use any technique you want unless I state in there that use this particular technique. You can use node voltage analysis, mesh current analysis, superposition, source transformation, Ohm's law, KCL, KVL. You can use a combination of all the tools that you have at your disposal. Okay. So for voltage, what do? Well, we have our open terminals, right? We have our open terminals. All we need to do is analyze the circuit and determine the voltage between those 2 nodes. And OC stands for open circuit. So that open circuit voltage is the Thevenin voltage for that circuit. That's all you have to do. So this is something that you have done before. Node voltage analysis, mesh current analysis, superposition. Any technique you take, doesn't matter what technique, you can analyze it using all different techniques, and you should be able to find the voltage between those 2 terminals. So the voltage between those 2 terminals is your Thevenin voltage. As I said, there's nothing new in terms of analysis that you're learning. Current needs a pathway to flow through. And so you place a short between those 2 terminals. And that short circuit current, ISC, is your Norton current. Your Norton current. So you analyze the circuit again, use any method you want, node voltage analysis, mesh current analysis, superposition, and you find the current flowing from A to B. That current is going to be your short circuit current or Norton current. And you can see why the circuit would be different. In the first circuit for Thevenin voltage, the output terminals are kept open. This one is a short. So the circuit will change. We will go through 1, 2, 3 examples, and you will see how and why a circuit would change. You place a short in there, circuit changes, right? So you analyze both of them independently of each other. Any result that you obtain in the first circuit does not apply to the second one. Any result you obtain from the second one does not apply to the first. Is that clear to everyone? And then finally, Thevenin resistance. Thevenin resistance is also measured at those same terminals. But if you have sources in there, obviously you cannot calculate resistance directly. So what we do is we reduce all the sources to 0, meaning we replace the voltage sources with a short circuit, all the current sources with an open circuit, and then all we are left with in the entire circuit is a bunch of resistors. Make sense? We reduce all the sources to 0. When they're all 0, the only thing that is left in the circuit is a bunch of resistors. The beginning of chapter 2, you learned how to find Req. Reduce the entire circuit of resistors down to one single resistance. And that is your Thevenin resistance. So Req is your RTH. And then you can verify your answer by using Ohm's law. VT is equal to, or VTH is equal to IN times RTH. Any questions? How many of you are taking the lab? Pretty much because of the class. This entire concept thing that I just talked about here, analysis wise, is going to take a long time. The 3 measurements in your class should not take you longer than 5 minutes. Trust me, it's not going to take you longer than 5 minutes. Just think about what you have to do. You power on your circuit, you have the multimeter, you place it at the output terminals, measure VOC, done. That's your Thevenin voltage. Then, keeping that same multimeter connected, you simply change the multimeter function to current, measure current. Automatic current measurement, done, Norton current. You don't even have to change or remove anything. Req, you simply take out the power supply, short the circuit out. Same, keeping the multimeter connected, Req. Should not even take you like 5 minutes, less than that. Anyway, if you have any questions, I'm around. Otherwise, I'll see you all on Wednesday. All right.